All right. I think we are rolling now. Okay, so this first section in Chapter 7 is called Integral as Net Change. And you guys kind of have seen some of this before. In fact, that one question we just got done talking about on your exam about the, there's one AP exam question I had thrown on your exam about the rate of water entering or leaving the tank or whatever. And you're looking for what's the change, how much was added or how much was removed and that sort of thing. That's kind of along the same lines as what we're going to be looking at with this as a net change. Today we're going to be focusing on particle motion as net change. So looking at this idea of how can we calculate the displacement the particle has moved. Okay, so what's the net change from where it started, like distance as net change. Okay, so if it started here, here's the equation for its velocity or whatever, so how far has it moved after so much time, that sort of thing. So we'll look at displacement that way, so how far from the starting point, but also we'll talk about total distance. So maybe we're more interested in not how far away from its starting point is it when it's done, but how far did it actually travel. So if the particle had a little like pedometer attached to it as it was moving, like what was the total distance that it ended up back and forth going or whatever. So we'll look at that too, okay? Chapter 7 in general is about applications of integration. We've done a little bit of application work, but we're going to really dig our teeth into it now. We're going to come back to area again. We're going to calculate areas using integrals. We're going to do all kinds of different areas. We're going to calculate volumes using integrals. So we're going to take like a function, revolve it around an axis so that it creates a solid. If you guys can kind of visualize that, think about taking like a parabola and then putting an axis underneath it and then revolving it around that axis. It makes like a big football kind of a thing. So we're going to take all kinds of different shaped functions, revolve them around different things, make these solids, and use integration to calculate what the volume of that solid is when we're done. So we're going to do some of that. We're going to do some applications from statistics. We're going to be doing some applications from economics, from some other science-related stuff like fluid pressure. So we're going to kind of open up into a lot of different stuff in Chapter 7. But we're going to go back to this particle motion stuff to kind of hit you back onto that idea. That's something you're used to, and then kind of work our way into the other stuff. So, okay. So, so we'll start with just some stuff just to kind of review and get you back on track here. Let's say we've got some particle and its velocity over time is 3t plus 5 for t greater than or equal to 0. And let's say that this is measured in we'll do inches per second. All right, so this will start to look a little bit like that one question from your exam as well, that other constructed response one that we did. All right, so let's start with this. Find the acceleration of the particle for any time t. So if the velocity was 3t plus 5, how do I get acceleration? Derivative, right? If you're moving that direction, position to velocity, velocity to acceleration, that's a derivative, right? Okay. So what's the acceleration then? Just 3, right? And then the units on that? inches per second squared, right. Okay, so what that means is that this particular particle that's moving along has a constant acceleration then, right? It doesn't matter the time. It's always going to have an acceleration of 3, wherever you're going. Okay? That was easy. Part B. Okay, so let's try going the other way with it then. Position of the particle for any time t if its initial position was at x equals 2. So what do I have to do to work my way to a position equation from a velocity equation then? Do the antiderivative, right. Okay. So s of t is found by doing the integral of v of t, or the antiderivative of then. Okay. So go back to your velocity equation up at the top there then. What is the antiderivative of 3t plus 5? Yeah, we'll put the plus c for now, but yeah, it's going to be plus 2. So, yep, so 3 halves t squared plus 5t, and then we got this constant. All right, now I had this extra information on here. I said the initial position was x equals 2. Okay, so that means that the position of this thing is supposed to equal 2 when time is 0, right? If it's an initial position, time is 0. So you can probably just look at it and say, oh, okay, so I need to put a plus 2 on the end. But here's the roundabout explanation here. So this needs to be true, right? When you put in a 0, it has to equal 2 as its position. So since these other two end up becoming 0, c is equal to 2. All right, so then you can get your equation. Your s of t is equal to 3 halves t squared plus 5t plus 2. Okay, so now that we have this equation, this opens us up to ask some other things of you now. So my part C to this question then is, what is the displacement of the particle on the interval we'll say 0 to, let's go 0 to 3. So what does displacement mean again? People that have taken physics, come on now. Displacement, what is it? Correct. Yes, the distance from the beginning. Okay, so where did it start at the beginning? What was its initial position? 2. Okay, so we need to figure out at time equals 3, where is it, and how far from 2 is it? Okay, that's going to be the displacement then. Okay, so S of 0 is 2. S of 3 is what? So if you want to use your calculator for a quick calculation, go for it. But go ahead and figure that out. What is S of 3? $30.5. We get a verification on that? We're good? Okay. So, starts at 2, it ends at 30.5. Displacement then is S of 3 minus S of 0, right? It's the difference between those two. So that would be 28.5. All right. So, if you know a position function, displacement is not too bad, right? Where was it? Where is it? What's the difference, right? If you don't know the position equation, okay, or you just haven't, you don't need to do it actually. If you consider the fact that a position equation is an integral of the velocity, okay? So, if I my displacement using velocity, I know it has to be the integral. So what do you suppose I'm going to do with that 0 and that 3 to find this displacement? It's going to be the integral from where to where? 0 to 3 of the velocity. This will also get you the answer. Okay? So it's the integral from 0 to 3 of our velocity, which was 3t plus 5. All right, now again, in the interest of time, if you want to just do this on your calculator, we should get 28.5 when we do this. As long as all our other math was correct up to this point. So let's try that real quick here. All right, so we get 28.5? Yep, should have. Okay, so you can look at displacement, okay? It is this idea of how far is it from where it started, but if you just have the velocity to work with, it's simply then just the integral of that velocity over that interval then, okay? Because that's going to give you that change in distance by doing the integral of that velocity, so you get the same answer, okay? Now, this other wrinkle to throw in here that we talked about earlier, we've got total distance versus this displacement. Total distance is like, if I for the ride the whole way, how far did it go total, versus this is just a change in, okay? So, I'm going to give you guys another velocity to take a look at, and we're going to work with that idea for this one, okay? by the way, I have to go back and do this, mostly because I'm being recorded, but these 28.5s, 28.5 what? What's the unit? Inches. I'd be remiss not to put that on there. Make sure I do all that correctly. Okay, anyway, back to the next one. All right, so let's say we've got a velocity. We'll try and make this one maybe a little bit more interesting than just a linear one. What can I come up with? We'll do, well, how about just x squared minus 4. Whoops, that should be a t, not an x, sorry. Talking time still, right? So t squared minus 4. And let's put this on the interval 0 to 5. Start with this. See if you guys can do the same thing you did before. And you can use your calculator for it, it's fine. All right, we'll do displacement again. Oh, and I should probably give you some units for this. So let's do this in, we'll go meters per second this time. All right, so go ahead and get me that. What's the displacement from t equals 0 to t equals 5? And then we'll talk total distance after that. All right, so what do we get? Or are we still working? 21.6 repeating? All right, 21.6 repeating what? Meters, okay. All right, so there's your displacement again. All right. So let's try the distance thing then. Okay. Displacement versus total distance is the difference of something that we've talked about before. Remember we talked about signed area versus total area? It's exactly the same thing. Okay? The signed area is what you just did with the displacement. Negative and positive can cancel each other out, right? Because when you go out a certain distance but then come back a certain amount of distance, do you see how there's things canceling out there? That distance you moved out and that distance that you covered coming back canceled each other out, and then it's ultimately just how far is it from the end. Total distance, you want to keep everything. You don't want things to cancel out as you go. So now we're talking total area, not just the signed area. Okay? So we need to figure out how much area is there above the x-axis and below the x-axis when we take a look at the graph of this thing. Okay? So that's what we're going to do next. We're actually going to look at the graph of this and think about what do we have that's above, what do we have that's below, and use that to help. Okay? So t squared minus 4 on the interval from 0 to 5. Oh, actually, I got to go negative on this thing too, don't I? A little bit. Okay, so this thing starts down at negative 4, and it's a parabola that takes off like that. Okay, and we go from 0 to 5. So let's say like 5 is out here somewhere, okay? I should make this actually come out a little bit more then. So this is not exactly to scale, but it doesn't really matter as long as we can get everything we need. All right. So we've got this area here and this area up here. And when we did the displacement, okay, negative area with part of this area up here, and then what was ever left over, that was your answer, 21.6. But now hold on to all of it, okay? So it's critical to know, where's that? Because we want to take that by itself. We want to take that second chunk by itself and then add those together, okay? So the equation is t squared minus 4. Where does it cross the x-axis? 2. Right. If you plug in a 2, you get 0, right? So this is at 2. So we're going to take this thing in its 2 chunks, do the integral of the velocity for each of the 2 chunks. Okay. So let's do the integral from 0 to 2 squared minus 4. See what we get. And then let's do the integral from 2 to 5, t squared minus 4. And let's see what we get. So again, if you want to use your calculator to speed up the process, totally fine. Okay, we can all do this integral by hand, I know that now, but for the sake of getting through this, just type it in. Huh. Yeah, I just figured that out too. Daylight savings. Yeah. Oh, that'd be nice. All right. So, do we get an answer for the first one so I can jot that down? What do we have? Okay. Get a verification on that? Anybody get the same thing? Okay. Second, we get an answer for that yet? 27? Okay. Verification on that? 27, 27? Yep, yep. Okay. So, distance, it's like total area. This negative right here is meaningless. I just want to know how much. I don't care if it's positive or negative, if it's above or below. I just want to add it all together. So you can kind of wipe away this negative or think absolute value of each, okay, and add it all up. So this total distance traveled then is 3 repeating plus 27. So it would be 32 and a third. Okay. So what these two individual integrals tell you is, at least with the negative and the positive, is this negative area, this first one, is at this point 3 meters to the left, and then it turned around when time was equal to 2, and it traveled 27 meters to the right. Does that make sense? Okay. The velocity tells you direction. If the velocity is negative, it's moving left. If the velocity is positive, it's moving right. So, and when you do the integration of those, it tells you how far it went. So it went this far to the left, this far to the right. So altogether, total, it traveled 32 1/3. Okay. Do you see how, though, that these would cancel each other off if I didn't think total distance, if I just wanted to know how far away from the beginning it was? Because this negative 5.3 meters, I would have gobbled up that 3 meters out of this 27, and then I would have been left with the answer we had for the other one, which was 21 and 2/3? Yeah, 21.6 repeating. Okay, so that's kind of the difference between those two. Now, if you are allowed to use a calculator, there's a sneaky way that you can get through this second one without having to look at the graph at all. Okay? If I went 0 to 5 of the absolute value of t squared minus 4 dt, what's an absolute value do to a graph of an equation? Or just think, what does an absolute value do to any number? Makes it positive. So, if I have the absolute value of my entire equation, wouldn't it just make all the parts that are negative positive? Right? And if it does that, wouldn't I have everything positive the way that I want, and then I would just add it all together and I would have my answer? So try that once. Type your calculator, do an fn int. You got to go grab the ABS, it's under math. But do the absolute value of t squared minus 4, the integral of that. Should come out to 32.3, just like we did with the other two separate. All right, yeah, it should look something like that. So double check it if you didn't get the right answer. So fn int of ABS x squared minus 4, 0, 5. Now, if you notice, there's a teeny bit of error here. Your calculator kind of chokes on this a little bit, but it should be enough where you can kind of see the trend and know what it should be. So, yeah. So we're getting the same thing then, 32.3 meters. Now, sometimes you have a calculator to help you with these, sometimes you won't. Again, we're going to do some stuff non-calculator, we're going to do some stuff with your calculator. So if it's a calculator question, don't make it more difficult than it needs to be. Just do this little trick and be done with it. If it's non-calculator, that's when things really get interesting because you need to know what the graph looks like to know where to put that point where the graph could potentially change from negative to positive, and then calculate each integral by hand and add those results. Okay? So we will do a little more practice with that tomorrow and into your homework and that sort of thing, but that's going to be something that we're going to be working on as well. Okay, I think for today, this is kind of a natural stopping point. I know we got a little bit of time, but I'm going to stop it right now. And because tomorrow we're going to switch gears a little bit, and I don't want to jump in just yet. So, schedule stuff, just so you guys know, tomorrow we're here. Wednesday will be your online day then, okay? We have a few more before I set you. Okay. So yesterday, just to recap, we were talking about taking a look at a velocity function and using that to determine with particle motion the displacement a particle was at the end of its journey and the total distance it had traveled. And what was the difference in how we calculated that when it was displacement versus total distance? Who can tell me?
Use the absolute value for total distance.
Right. Yep. So absolute value for total distance, or if you're looking at the graph, what did we do for total distance?
Total area.
It's just the total area versus the signed area. Exactly. Okay. So keeping that in mind, all you really need is a graph that you can find the area under different portions of it, right? You don't even need to know what the particular function is to be able to do this stuff. So we're going to start with that today, so using graphs to calculate displacement and total distance, and see if you guys can do it without having a function to work with here. All right, so let's say we've got this function, and this is going to be time, and this is going to be velocity. And let's say this is at 5. Okay, and then I'm not going to tell you the function for that, but we have some area here. So let's say this is 12, this is 8, this is 10, and this is 3. Okay, so I want you to calculate what is the displacement from t equals 0 to t equals 5. And then what is the total distance? All right, so take a look at that graph and see if you can come up with those two things then. What's the displacement from 0 to 5? What's the total distance from 0 to 5? All right, would anyone like to share what they came up with? Start with displacement. So how would I go about doing that with this information here? Exactly. Take the areas above and subtract the areas below. So we've got 22 on top. We've got 11 on the bottom. So what's the displacement? 11. Okay. And I didn't tell you what kind of units we were using, so we'll just say 11 units, whatever it was, inches, feet, meters, whatever we're talking about. Okay, what about total distance then? Just add them all up, right? What do we get when we add them all up? What was it? 33? Yeah, it should have been 33. Okay, so gonna expand on this just a little bit then. If the particle started at x equals 5, where is it after, and we'll say this is in seconds just so I can write this question. So if the particle started at a position of x equals 5, where is it after 5 seconds? So what am I going to use to answer this question, the displacement or the total distance? I want to know what is its location after 5 seconds. So what do you guys think? It's displacement, right, yeah. I don't care about how it got there, right? I just want to know where it is. So that's a displacement question. So what am I going to do here then? If it's starting at x equals 5, I need to use displacement. Where is it? Don't overthink it. It started at 5. Its displacement is 11. So where does it end up? 16. Yeah, exactly. Okay. So it'll be x equals 16. That would be its new position. So think about, again, we're trying to think of this as a particle that's just kind of moving back and forth on a number line. Okay? So if it started out at 5 and its overall displacement was 11, it's going to move down that number line 11 more from 5, so it's going to be over at x equals 16 when it's all done. Okay. All right, so I'm going to put in some other little t-values in the middle here now. I'm going to ask you some more questions about some other stuff. So let's say if this is 5, maybe this is 4, this is 2, and this is 1. Okay, those are all t-values, and they're not to be confused with the 12, the 8, the 10, and the 3. Those are areas. Okay. So let's try this then. Again, using the graph to help us answer this question. Where is the particle the furthest from the origin on that interval 0 to 5 then? Okay, and remember, we're thinking about this particle just moving back and forth on a number line. So when I say origin, I mean just 0 on that number line. So where in that interval is it going to be furthest away? How would I figure that out? At t equals 4, okay. So why do you say t equals 4?
Because it's just like, if you stop and go, or the highest there,
Mm-hmm.
you'd add more in there because, minus 8, I add 10, so you'd add 2 more.
Exactly. Yeah, so you want as much positive area accumulated as you can, right? Okay, so each one of these points, 1, 2, 4, 5, you can think of those as potential places where it could be the furthest away. Does that make sense? Because that's when you've had the most positive or the most negative area put in there. Okay, and you just have to kind of think about it from one point to the next. Where am I at? How far have I gone? So from 0 to 1, like 0, you're still sitting at 5, and then you add 12 to that, but then you subtract 8, but then you add 10, but then you subtract 3. So which one of those stopping points is giving you the most positive? Okay? Or I guess technically it could be the most negative as well, but in this case there's more positive than negative. So you start by 12 when you get here. Then you subtract 8, you're down to 4. You add 10, you're up to 14. So now we're at more than 12. So far 4 is winning. And then we subtract 3, and so we're back down to 11. So t equals 4 is going to be that place that we want then. Yeah, that's going to be the furthest. Okay, so that's what you want to kind of think about when you're dealing with that sort of thing. I think that's about all I want to do with that. Nah, I won't do that. There's one on your homework to ask you one more thing, but I'm going to let you just look at that because that's, yeah, I want you to think about it on your own. The other thing we want to talk about today are these consumption problems and doing net change from data. So if you have data in a table, again, you don't have a function to work with, but instead you have some data that you're looking at. How do you mess with that? So let's start with the consumption stuff first. We'll work back to the data stuff, and then we'll be done. All right, so consumption. Stealing an example out of your textbook because I thought they did a good job with it. So if you want to follow along there and you don't want to write it all down, you don't have to. It's on page 383 at the bottom. It's example 5. But in any event, the question is like this. It says from 1970 to 1980, the rate of potato consumption in a particular country was given by this. Okay, so they found an exponential model apparently for the consumption of potatoes. And this is in millions of bushels per year. Okay, so think back to your exam. There is that one about the water, right, where it gave you the rate that the water was going in, the rate that the water was going out. You can think of this as kind of like a velocity. This equation is measuring a rate of change, right? Just like a velocity measures a rate of change. Velocity is meters per second or miles per hour, something like that. It's always a certain amount of distance per unit time, no matter what you have for velocity. Consumption ones, it's the same thing. It's instead of consuming distance, you're consuming something per unit time. In this case, it's bushels of, or millions of bushels of potatoes. But it's the same idea. Does that make sense? You're eating up something, no pun intended, per unit time. Okay? Anyway, so you think of that as, like I said, like a rate. It's kind of like a derivative then, right? Think of this as kind of like a differential equation in that way. But it doesn't have the little prime or any of that kind of stuff on it, but you just have to kind of think of it that way. So that's millions of bushels per year. T is, what is it? It's in years, I believe. Yeah, T is years after 1970. Okay, so if you're going to do 1971, you'd plug in a 1. 1972, plug in a 2, that kind of a thing. So they want to know how much were consumed from the beginning of 1972 to the end of 1973. Okay. So how much time are we talking here then?
2 years.
A 2-year period. Okay. So just kind of file that away because we're going to come back to that. But if I want to know how many bushels, I'm not asking for a rate, right? I'm not asking for how quickly were the bushels being consumed. I'm asking for just how many bushels. This is just like figuring out displacement or total distance, that sort of thing, right? With displacement, total distance, I don't want to know how quickly the thing was moving. I want to know just how far did it go. It's the same kind of idea, except now we're just talking millions of bushels of potatoes. So just like before, where I had to do an integral of the velocity to figure out the distances, now I need to do the integral of the rate equation to figure out how much was actually consumed. Okay? So it's going to be an integral of this consumption equation. But then I'm going to go back to what I just asked you before about, okay, how long a period is this? It's a 2-year period. Don't let the information here throw you off. What should be the limits of my integral?
Should be like 72 to 74.
Essentially, it's 72 to 74. If we think of 2 as being the beginning of 1972 and 4 as being the beginning of 1974, That's really what we want, right? End of 73, beginning of 74, it's the same thing. So our limits on here are going to go from 2 to 4. That's what we want. Because remember, T is years after 1970, right? So 2 to 4 should make sense then. Okay, this is one. I'm not sure we're going to be able to do the antiderivative by hand necessarily, so let's go ahead and just do our calculators on it. So if you would, do your if and int on that equation from 2 to 4. See if we can get the same thing here. So take a minute, calculate that for me. All right, what do we get? Like a shade over 7, right? 7.066 or something like that. Okay, 7.066 what? Yeah, millions. So it's 7.06 million bushels of potatoes. Okay. It's really that easy. Consumption, you figure out what is the rate equation, do the integral of that over the appropriate units depending on what the time period is that they give you, boom, got it. Okay? So, but I can't stress the importance of that enough because we're going to come back to this idea again and again that the integral of the rate equation is the amount of stuff that you get. Okay? We will talk a lot about that in the future. So, I don't want to spend too much time on that because I think you guys can do that. So then the net change from data. This one I want you guys actually to open up your textbooks and take a look because I don't want to write down all the numbers. So page 384, if you would, please. Go take a look. Should see example 6, like right in the middle of the page. Okay, page 384. Try to get their solution for the moment, but just look at the data. So here's what I'm going to go ahead and read it to you. You can read it too if you want. That's fine. The generator operates at a varying rate depending on how on from the generator to operate the machinery. The rate, gallons per minute, at which the pump operates is recorded at 5-minute intervals for 1 hour as shown in table 7.1. How were pumped during that hour? Okay, so take a look at the table there real quick. It's got the time from 0 minutes all the way to 60 and what the rate of the generator was at that moment. Okay? We need to figure out how much was pumped. So if I had an equation for this data right here, it would be the integral of that, right? Does that make sense? Because these are all rates that they're giving you in this table. So the integral of that rate equation would be your total consumption. But we don't know what that equation is. We only have is this table. So if all we have is data, what do we got to use then instead? What have we done in the past to find area under a curve if we didn't have an equation to use? Yeah, we could do a trapezoidal rule, Simpson's rule, something like that. RRAM, LRAM, something of that nature. Okay. So, and MRAM. Yep. So at that point, it kind of becomes what you want to do. I think whenever I'm given data like this, the trapezoidal rule makes the most sense in my head because I would want to just connect the dots and then make a bunch of trapezoids and then go that way with it. Okay, so that's what we're going to do. Okay, so the trapezoidal rule Okay, this is the one where it was, make sure I'm doing this right, it was n over 2, and then it was y0 plus 2, y1 plus 2, y2, etc., 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 until we get to the last one. All right. So, for us then, the integral from 0 to 60 rate, and we'll call it r of t, means we're going to need to then take the data and then use it into this table over here. Okay? So, this is not n, this is h. That's the height. Sorry. So, what is the height of each one of these trapezoids? Look at your table. What would be the height? 5, right? Remember, these trapezoids are kind of like sitting on their sides. So the height would be like the spacing in between each one of them. So that h is going to be 5. So we're looking at 5, 2. And then it's just pulling the data off the table there. So the first one we had was 58. And then we had 2 times 60 plus 2 times 65 plus 2 times 64, etc., etc., until we get to the last ones, 2 times 63 plus 63 is the very last one. Okay, so all the way across there. Take a minute. I want you to type this up on your calculator real quick, and let's see if we get the same thing. So this is our best approximation we can get based off of the data in that table then. See if we end up in the same place here. All right, here's what I got. So if you got something different, you missed 1 or 2 from the table there. It's easy to accidentally skip some, but I got 3,582.5. Okay, so it's 3,582.5 what? Gallons, yeah. Yeah, so the total amount, and it says at the bottom here, the total amount pumped during that hour then is about 3,580 gallons. So, got it. So, all right. Yeah, does this stuff make sense, guys? Think we can do this? The consumption and the total distance versus displacement and all that jazz. And really the only difference with this table stuff is if you don't have an equation to use or you don't have a graph to use and can't find the areas, then it's just doing some kind of an approximation like we've done in the past. And trapezoidal rule is going to be pretty safe. If you just want to stick with that, it'll work fine. So I'll let you guys get to it then. You got a little bit of time here in class. You got the day tomorrow, online day, so plenty of time.